Okay, so for the hands-on experience here, we want to go through some of the techniques that we discussed for the concept part, theory part in the video, and then we want to see how can we use this model and techniques. So here, if all of you have access to it, there are a few things that are important here. That's why we're going to use them one by one in the future. But the first task for me was creation of synthetic data. Like, it can be as simple as an array of number with having maybe one weird number in it, as simple as that, or making like a bit more complex, like a normal distribution, and having like a 2 cluster of data and moon that if you want to visualize it, then you should be able to see. So here in the first one, you're just saying that all the points happening in the middle and the rest of them are maybe anomaly or outlier. They're not maybe from the main distribution. The second one is if you have maybe 2 peak in your data, and then you want to say that if you can capture the rest of the point. And the third one was if you have a bit more complex pattern in your data, can you find those anomaly around it? So this is going to be like a 3 basic synthetic data, of 4 actually, that you want to see that can we find those points using all these models that we're going to talk about. So even when we talk about maybe more complex model, like I don't know, 1SVM or isolation forest, all those things, we'll use these data as well so we can compare actually to see what is the difference between them.
So then the first 2 will be best for density-based model, right?
Probably, yes. We will see. You never know, but you're right actually. So it means, okay, depends on the prior distribution that you're thinking. If you're saying that about the Gaussian one, yes, you should be able to capture them a lot better than the other techniques. But for the third one, maybe just fitting a Gaussian is not enough, because then you will miss all those points in the middle, in between. So maybe you need a more sophisticated technique. So yeah, I was just trying to get familiar with all this data, and then how can you plot them, because we will do that lots of time, but we'll just add more label to all these points so we can actually say that what's the difference between normal and not normal one. So first thing first, going to be a Gaussian technique. So it means there's like a 2 function that I wrote. Is like the first one is like giving maybe let's say a data set. We'll try to compute the mean and variance per dimension. And the second one, with the assumption that all those Gaussian models that you have generated are independent from each other, if you try to compute the probability of it. So basically, the thing that we are doing is we are fitting the Gaussian model by just computing the mean and standard deviation, and then using that, we can compute the probability or likelihood of that sample. And if you have multiple dimensions, or if you can fit more a mixture of those models, then we can combine them and then use maybe the multiplication of all those probability to see what is the probability of that point in your data set. So you can say that these are kind of like a generative model that you want to learn the distribution of your data. Once you learn that, then you want to say if something is wrong or not. One of the important thing here is we'll see that, but they will work better if we are dealing with semi-supervised data. Like if you have lots of outlier, then they can change the distribution, change the standard deviation in a way that you might miss some of them. So we'll try to see them actually, but first thing first, as I said, going to be just computing using the estimated Gaussian. You should be able to compute the mu and sigma, and then you can come with the standard deviation. And as I said, if something is 3 times after the standard deviation from the average, then you can say that maybe that thing is anomaly. Here I use 2 instead of 3, and then you can, okay, as an exercise here, I just want you to actually play with that number and see what's the difference. So for 2, you can say that what happens if I just use the 2 standard deviation from the average, then it will say the first number and second number is normal, but the third one is not, and the rest of them are normal. And if you wanted to compute the probability or the likelihood, you can see that for the third one is almost like 10 times lower than the rest. And if you look at the data, the third one is like 100, but the rest was kind of around 1. So just by computing a standard deviation of the data, you can just manage to find all those outlier or anomaly which the value of the data is too far from the average. Just as simple as that, you can just find some of the simple anomaly that can happen in your data. Sometimes, because we can say even sometimes or even most of the time, the data or the anomaly is not a result of an intelligent source like a human. Sometimes it's just maybe an error in the system, or maybe a data entry problem, or maybe let's say even for health insurance, usually you're providing cost. But if you forget to do that, or the one who's doing the entry forget to do that, the cost will be 0. And having 0 as a cost of a claim is weird. And the easiest way that you can capture all of them is just by using something as simple as that. Then you can kind of capture all those claim or all those things that they are different from the rest of the data. So sometimes you don't need complex model to be able to find anomaly. So here at the first part, I was just trying to say that those complex model that we'll talk about is not always needed, and based on the type of your data, you have to choose the model which is more appropriate. So then here you can actually, as I said, you can play with that number. And can you just use 3 as standard deviation to see what will be the result?
No.
What is the result?
No, but then isn't that the 1.96 is already 95% confidence interval, right?
Yes.
So then 2, then if you beyond 2, then it will be like really rare.
So if I use 3, what will happen?
Everything.
Why everything?
Because the distance would be, I mean, the distance for 100 is not that much from the mean, right?
So the thing is, if you look at this data, you can visually say this is like super different from the rest of them. But if you feed a Gaussian, usually they're using actually if you look at all those textbooks, they're saying that okay, 3 standard deviation is the norm, is the one that you should use to be able to find the anomaly, because then you will cover 99.7% of the data. The rest is fraud. The rest is not normal. Then here you can just by using it, you can just say that if you use 3 standard deviation, will cover all of the data. Then nothing is abnormal in that array. Then you need maybe 2 standard deviation. And then we can say 2 things here. First of all would be if I remove that 100. So if I treat the data to be clean, so then changing that problem from unsupervised to semi-supervised, then fit a model. Then 3 standard deviation will work or not. Even 4 or 5 or whatever I use will work, right? Because then I'm learning the distribution of the data, the clean data, and then 100 will be far away from the normal data. But if that anomaly is part of your data, and if number of data that you have is not that much, then just by using generative model won't be enough.
I think you're right. The number of data points you have here is very important.
Yes.
Since you have just very few of them here,
Exactly.
you have to remove it to be able to.
Yes. So that's why for me, that's like an extreme case of it. It means you should either add more items here, more value here, but you might add more anomaly as well, right? So if the ratio of anomaly to the normal, noise to the normal, is too high, then doing any kind of generative model, learning distribution of data won't be enough. Then maybe you have to do other techniques. Maybe you have to do other things. But the thing I was trying to do by that simple example is everything depends on your data, and most of the generative model, like doing GMM, because GMM is like in all the textbook that you can just use, apply, and then you can play with it. So it's like a straightforward and simple model that you can and you should use. But the thing is, always you should be cautious, and you should learn your data first, because the assumption of all those generative model, like all those GMM, which is a mixture of Gaussian model and all these models, is like your data should be clean. You should learn the distribution of your data, not the data with noise. And even if you want to play with that, you can make a new, for your maybe own exercise, you can add more data and see when the number of data pass what threshold, then maybe serious standard deviation going to work. Maybe it's like as your homework, you can just say that what should be the ratio of maybe data, what is the relation between the value and the number of data that will make the serious standard deviation work, which is like a norm whenever they're trying to find anomaly.
So we can approach this sort of problem using two different scenarios. So one might be just fitting our generative model and using the parameters of distributions we get. Other might be filtering out outliers first, using somewhat more sophisticated algorithms, maybe some ad hoc manual techniques, and then fitting generative model when we have more confidence that there's less anomalous data in the distribution, and then do that. So is this approach used in practice or not?
Yes, exactly. Maybe, okay. That's why we have supervised, semi-supervised, and unsupervised one. It means So one of the things that I was saying is like the difference between semi-supervised and unsupervised is your data is clean, and for most of the techniques that you are using in practice, their assumption is the data is clean. So it means for all those generative models, yes, they want to learn the distribution of the data, and then if the likelihood of your sample is off, they will say you are anomaly. And you even tried, if you use 2 times the standard deviation, you should see here is a clear picture that the probability is 10 times lower, and you can say, okay, this is actually fraud. So the model was successful here if I use 2 standard deviation. So it means, was it successful? Yes, but you have to change it. You have to lower your threshold, and and then it means the only thing is like if the data is not clean enough, it's hard to clean the data. But if data is not clean enough, just relying on the first model that you can get from any places and applying that model won't help you. It means you have to learn why you are using a technique. It means if it's generative model, the underlying assumption is you are learning the distribution of data, and your belief is the data is clean. And if it's not clean, then maybe you have to play with all the threshold. You have to manually change something. You have to do something. So if I don't use that, if I just apply like a box of maybe a GMM model, just say fit, and then get the probability, can I just rely on that? Maybe yes, maybe no, if I don't know what's going on inside. So that was maybe my main message here. Any question? Going for it.
Yeah, so if if we assume the data set is clean already, then there's no need to do anomaly detection on the existing data set, right? So in this case, it will just be for new data
Yes.
that comes in.
Yes. So that was the whole point of all those semi-supervised model. The assumption is the data that you're giving me right now is clean, is normal. Maybe for autonomous driving, you're going to different, I don't know, there's a sensor in a machine driving different street, or you're recording signals from your device, or is a stock market which is normal. You know it's normal. And then you want to learn the distribution of it. So in the future, if you see something which is not similar to the thing that you have seen before, is deviate from your standard assumption, then you can say, okay, that's maybe fraud, maybe that's abnormal, maybe that's maybe outlier. So that's kind of like a base assumption of it. And it's not like it should always be clean. That's why I tried 2 here, and it said that it's work. So it's not like it's not going to work at all, but you should have it in mind that it will try to learn the distribution, and if the value of that error, if I put maybe 10,000 instead of 100, then maybe even the second one might not work, or maybe it won't work. See, even maybe the value of anomaly can change the thing that you're going to fit. So, okay. Second one. You have 3 synthetic data, and you do have 2 functions which can compute the mu and sigma, and the second one can give you the probability of it. The thing that I want you to do is to find anomaly using these 2 functions that I just used for the numbers on these 3 datasets. Can you just fit a Gaussian model on these 3 and see what kind of anomaly this will cover? That's maybe the actual exercise for Gaussian model. And for sure, as an example here, I've done that for norm. The thing that you want to do is what will happen if you add, I don't know, if you play with the different things.
Using univariate Gaussian model. Univariate Gaussian.
Yes.
On which? How do we project it? Or do we use bivariate?
If you just use that function, per dimension it will compute the average and the variance. So the per dimension you're getting the probability or the mu and sigma, and then by computing the p you should be able to get the probability, which the assumption of that function is all those dimensions are independent from each other.